Welcome to IMS2020 Microapps. My name is Rafi Hershtig and I'm CTO of KNL Microwave. Today's topic is tunable and fixed filtering solution enhances dynamic range of harmonic and IMD measurements for 4G, 5G LTE bands. The motivation of this talk is to review basic filtering solutions that in one configuration or another we can increase the dynamic range of our setup. It is a versatile approach where we can customize the solution for any specific bands. Harmonics, IMD measurements, blockers, carrier aggregations are only some of the tasks the engineers today are faced with. I hope that in this presentation, new ideas will come up and we will be able to improve the way we measure devices. The first example is of emission monitoring solution. The spectrum coming from the device under test, such as an amplifier, is showing on the left. Carriers are shown in red, IMD products and harmonics in black. We're positioning a high-pass, low-pass to divide the spectrum into near zone and far zone. Following the low pass, there is a bandpass bandstop Duplexer. The bandpass is terminated by a 50 ohm termination. As the spectrum enters the first high pass low pass, the carriers are traveling through the bandpass and the IMD and harmonics are traveling through the band reject. Spectrum analyzer is positioned to switch between the near zone and the far zone. In this way, carriers are prohibited from entering the spectrum analyzer and it's safe to operate the test. Here is another example where we can use bandpass bandstop Duplexer. For load pull test, the amplifier is on the left and the idea is to change the load for the carrier so that we can observe the impact on the second and third harmonics. Positioning the complex load behind the bandpass will guarantee that only the carrier's frequencies are being modified. In this way, the spectrum analyzer again is safe to operate and carriers are prohibited from entering the spectrum analyzer. One of the most frequent usage of high-pass, low-pass duplexer is for second and third harmonic tests. In this example, it is required to inject a carrier into the device under test and measure the harmonics generated by. Depends on the magnitude of the carrier, a PA is often needed. However, the PA itself produces harmonic. Therefore, the first high-pass, low-pass on the left takes care of this problem. Harmonics from the PA are terminated through the high pass. The carrier travels through the low pass into the device under test and into the output low pass terminated. Harmonics generated by the device under test travel through the output high pass into the spectrum analyzer. For powers in magnitude of hundreds of watts, special high pass low passes duplexers are designed. In this example, we have a low pass from DC to 2.2 GHz and a high pass from 2.8 to 6 GHz with power handling of 300 watts CW. In the next slides, we will analyze the case where we are testing our device due to blockers. The blockers represent signals of systems that are already deployed and operate in the field. The TX signal is injected through the filter, and the blockers are injected through the band reject. The purpose is to measure the IMDs in the RX band. This measurement is done in the reverse mode. The device under test is located at the common of the triplexer. Here is the actual data of band 2, a triplexer whom we just examined in the previous slide. The TX band is from 1850 to 1910. The receive band is from 1930 to 1990, and the list of blockers include 80, 1800, 3800, and 5800 MHz. Both bandpass filters for the TX and RX are diplexed and diplexed again with the band reject, providing 75 dB of isolation. The upper frequencies of blockers at 3800 and 5800 are passing through an additional diplexer shown on the graph on the right. Overall, we see that the return loss is nearly 17 dB, which provides a perfect match to the device under test across all the frequencies. Measuring the purity of the triplexer, we terminate the common with a low PIM termination. We then inject a TX1 of plus 26 dBm at 1855 MHz and a blockers at TX2 of plus 16 dBm at 1775 MHz. Connecting the spectrum analyzer to the RX filter, we measure the third IMD of 1935, which is 2F1 minus F2 of minus 147 dBm, a very low and respectful level with a very high dynamic range. The growing number of LTE bands and the lack of one system measures all there is a need for a versatile system where it's expandable and it's budget dependable and more bands can be added upon request. This low-cost solution is based on the idea that high-ticketed components such as amplifiers, signal generators, spectrum analyzers are found in every lab. In our approach, the fixed filtering solutions are connected together via switch matrices and couplers. In this way, we can maintain a very good dynamic range and a low-cost solution. In this example, we have a quad-band low PIM test setup. Band 3, Band 8, Band 40, and Band 42. The unit enclosed in the dashed blue line is one system, and all the peripheral equipment is supplied by the customer. Carrier aggregation is a very powerful feature. It allows transmit signals from different bands to be injected into the device. The purpose of this measurement is to inject those signals and find the IMD products in the RX band. CA7342 stands for carrier aggregation TX1 from band 7, TX2 from band 3, and RX band from band 42. In this example, the multiplexer is connected back-to-back to the device under test, performing reverse and forward measurement, allowing the device under test a broadband match from DC to 8 GHz. Up to now, we discussed monitoring the emission coming from the device under test. We now turn to a similar problem, but a little bit up the chain. The need to combine several transmit signals without creating IMDs. In the diagram on the left, there is a low-cost, broadband, and easy-to-install combining network. Two amplifiers, each provides TX signal, are combined via a 3 dB hybrid quadrature. This 3 dB hybrid quadrature must be a low PIM device. You need to specify it up front. We then pass the combined two signals into a band reject filter which is connected to a bandpass filter and cascade. Our goal is to create a versatile system where the transmit signals can be swept over a broad band range. The only condition is that the mixing product of the third harmonic or the fifth harmonic always lies in the band covered by the bandpass. So instead of combining the two signals and injecting them into a bandpass, which we normally do, this IP, this KNL microwave IP, suggests that if we do the opposite, if we inject the signals through a band reject, we can then get a very broadband system. If injected into the bandpass, there will be no way to sweep the signals too much, only few megahertz. Having said that, the bandpass bandstop is a very important building blocks in a broadband versatile IMD test box. In this example, we're looking at band 2 again, with a band pass around 1930 and 1940 MHz, a band reject around 1930 and 1940 MHz as well. This time, we have TX1 and TX2s on the low band and TX1 and TX2s on the high band. Every time TX1 and TX2 is injected, the third in the modulation product falls within the bandpass. The data below suggests that we can achieve minus 145 dBm for input signals of plus 30 dBm. That is a minus 175 dBc dynamic range. Another interesting feature of the bandpass bandstop duplexer is that we can achieve almost no change if the common port is 50 ohm terminated or opened. This suggests that there are no IMD sources within the bandpass bandstop that otherwise phasing might change the amplitude. LTE modulation bandwidth comes in 5, 10, 15, 20, and 40 MHz. LTE bands are spread from 600 MHz all the way to 6,000 MHz. If we to accumulate fixed filters for every combination, we would need 3,600 fixed bandpass filters and 3,600 fixed band reject filters. This gives rise to tunable bandpass bandstop duplexers. In the diagram on the bottom left, we see two identical tunable bandpass filters connected via 3 dB hybrid. The incoming signal at port 1 to the left, frequencies within the bandpass are going to be absorbed in the 50 ohm terminations, and frequencies outside the passband of the tunable bandpass are going to be reflected back. They will come out of phase at port 1 and in phase at port 4, which enable them to continue and travel through the isolator into the tunable band reject filter. In short, we are getting a two-port device that acts as a tunable bandpass bandstop. Top left is the data and data from memory of a bandpass bandstop at 750 MHz, then at 850 and then at 950 MHz. All along, this unit can cover from 700 to 1000 MHz. This unit, bottom left, consists of 3 tunable knobs, and it also allows you to measure the harmonics up to 4 GHz. It is available as a demo upon request. This unit is a digital controlled tunable bandpass filter from 4 to 6 GHz and consists of 9 sections, The bandwidth is between 1 and 2%. Datasheet is available on knlmicrowave.com website. The following unit is a very interesting one. It's a digitally controlled adjustable bandwidth. It can change the bandwidth and it can change the frequency of operation. From 700 to 6000 MHz, this is a digitally controlled bandpass filter. The unit is shown on the top right. The inside architecture consists of 4 stages. On each stage, there is a tunable bandpass filter that covers 700 to 1000, 1000 to 2000, 2 to 4, and 4 to 6 GHz. The mode of operation is shown in the YouTube movie and can be reached in the link shown above. While it takes a team to develop a test box, we will support any user interface required. Here is an example of user interfaces that are possible today. Thank you for listening. You have been a great audience. For further questions, please email me at rhershtig@klmicrowave.com. See you next time.